Good morning, yes, respected professors and colleagues. I'm really happy to explain my article at the Climate Resilient Agriculture for Asia 18th TSAE International Conference. My name is Mirjalal Ismailov, and I did this article with my colleagues, and their name is Islam Kadirov, Jamshid Shamuradov, and Bakhtiar Kurambayev, and the last one, Anarbek Masharipov. Today I will present our research on theoretical justification of the kinematics of a blade rotational drum. As you know, agriculture is one of the fields most affected by climate change. And to ensure food security, we must improve not only crops and the cultivation methods, but also very machines and tools we use in farming. One of key machines in soil preparation and crop management is a rotational drum with blades. In abstract, I will try to explain everything in a detail. Our study focuses on kinematics and energy efficiency of rotated drum blades used in soil tillage. We developed equations of motion to analyze trajectory of the drum blades under different rotational parameters such as angular velocity and the rotation radius in the cycloidal motion types. Our mathematical modeling shows that cycloidal motion is a key, which it minimizes soil resistance, reduces energy consumption, and at the same time improves soil loosening and aeration. Compared to traditional tillage tools, rotated drum machines can significantly lower traction resistance and the energy use, while enhancing soil quality and weed removal. The main takeaway is that optimizing blade design and drum parameters leads to higher efficiency and better soil processing. In the future, field experiments will be crucial to validate these theoretical results under real agricultural conditions. In introduction, I will start from soil preparation. As you know, soil preparation is essential in agriculture and includes operations like loosening, harrowing, and leveling. Rotary tillers with rotary working bodies are very effective because they need less energy and they can cut or break soil layers more efficiently than passive tools. As you know, the key element is a rotor, and which can work in two ways. First one is active rotation, powered by tractor engine, and the last one passive rotation, driven only by soil and tractor movement. Understanding the kinematics of these rotary drum blades is important to improve energy efficiency, soil quality, and oil productivity. In the materials and the methods section, we analyzed kinematics of the rotary drum blade under controlled conditions. We developed equations of motions to calculate the trajectory of the drum center and the blade path, considering angular velocity, rotation radius, and the cycloidal motion types. For the modeling, we used classical numerical methods, supported by analytical mechanics and computational mathematics, following Pano's theoretical developments on soil loosening. The main idea is that soil can be loosened most efficiently through tensile deformation. Since the soil has a tensile strength of about 5-6 kilopascal and the compressive strength between 65 and 108 kilopascal, loosening it through tension requires less energy. Therefore, optimizing rotor traction speed and load conditions allowing tillage machines to minimize energy use while effectively breaking the bonds between soil and particles. In the result and discussion section, we show that cultivators with passive working bodies face problems at higher tractor speeds such as increased soil resistance, higher energy demands, and wheel slippage. Simply adding weight to reduce slippage only compacts the soil, which is not desirable. In contrast, rotary tillage machines demonstrate lower traction resistance and better soil quality. They also meet agricultural standards, loosening soil more effectively and remove weeds, especially in heavy clay and peat soils. We also observed that using rotary tillers reduces number of passes needed, which saves both time and energy. Finally, The rotary drum blade itself works as a passive body but achieves effective soil processing through self-rotation under controlled conditions. As you can see, here we can see the schematic of rotary drum with blades. As a center marked as a O is the axis of rotation. R is represents radius of drum. The drum rotates with angular velocity, while tangent velocity of the blade tips is shown as Vm. The parameter 2 alpha indicates the angle between two blades. Va is the initial velocity of soil or water jet interacting with blades. Finally, h represents initial height of medium, which in practice can be soil depth or water level, depending on the operating environment. If you pay attention, you can see there is omega. We can see it's like an angular velocity. It helps us to understand how rotational speed, blade angle, and the trajectory of drum influences soil loosening process. By adjusting these parameters, we can reduce resistance forces, minimize energy use, and improve soil preparation efficiency. In the second figure shows that the rotary drum blades move and interact with soil. If drum were completely solid, the blade tips would follow perfect circle, but in reality, since the blades are spaced apart, each blade follows cycloidal trajectory, shown by curved passes. These passes are marked by sequential centers O1, O2, O3, with blades points A1, A2, A3. Instead of forming perfect circles, the tips form non-ideal cycloid, which varies depending on the soil resistance and blade spacing. The, the key element is cycloidal motion reduces soil resistance and energy use while still achieving effective soil loosening. As I told in the as I told as I told in the beginning, figure 2 illustrates the control unit and the interaction between rotor blade and soil. And so I will continue by jumping next page. In the figure 3 explains how cycloidal trajectory is formed when circle AB rolls without slipping along surface. If we take a point like E1 inside the circle, its path forms shortened cycloid. If the point is outside the circle, like E3, the path becomes stretched cycloid. The radius and the rotation determines the exact curve. Mathematically, trajectory can be described by a set of equations shown here. The main point is that the rotary drum blades follow cycloidal paths, which can be shorter or longer depending on blade position. This explains why cycloidal motion is so effective for reducing soil resistance and saving energy in tillage. As you can see, it's like a drum blade drum blade rotation diagram. In conclusion, we found that the blades follow cycloidal trajectories and these paths play key role in reducing tractive resistance, lowering energy consumption, and improving soil loosening. Theoretical modeling confirms that when drum operates along elongated trajectories, it ensures higher quality tillage and better removal of plant residues. Overall, rotary tillage machines with active rotary drum show superior energy efficiency and soil processing quality compared to conventional methods. The cycloidal motion plate is essential in balancing energy savings with effective soil preparation. Finally, we can say that the future work should focus on optimizing blade design and validating these results through field experiments so that theoretical predictions can be applied in real agricultural conditions. As you know that we need more experiments which we can do in real life. Thank you for attention.